which can be solved in a couple of lines. Namely that if the utility function is concave, and has no maximum, okay, which for concave functions no need to distinguish between local and global. And V is convex, then the demand is monotone. Okay? And as I said, this result is essentially due to a French economist called Millerand, who never published it. It's in a pre-publication dated something like 1974, which I discovered. And in fact, it's not a paper on monotonicity of demand. It's a paper on econometrics, but somehow monotonicity of demand enters in the picture. But this result is a substantial refinement of his result. I removed unnecessarily stronger assumptions, and I simplified the proof. The proof is extremely simple, as you will see now, but I wouldn't say it's immediate. Have you tried? So it's a simple proof, very easy to understand, but I wouldn't say it's a routine proof. So we will directly prove monotonicity by considering P and Q two price vectors, and X and Y in the corresponding demand sets. We have to prove that P minus Q, inner product X minus Y, is less than or equal to 0. Okay? And then I consider 1/2 X plus Y and I take U of it. Since we are assuming that U is concave, this is greater than or equal to 1/2 U of X plus U of Y. But X is optimal under P and Y is optimal under Q. So U of X is equal to V of P. Okay, the objective function is the optimal value, and the optimal value is called V of P. And U of Y, for the same reason, is equal to V of Q. And V is assumed to be convex. So this is greater than or equal to V of 1/2 of P plus Q. We are almost finished. So from the inequality we have obtained, I conclude that 1/2 P plus Q inner product 1/2 x plus y must be greater than or equal to 1. Do you agree with this? What's the assumption that guarantees that this inequality holds? What have we used of the assumption so far? Concavity of U, convexity of V. Sometimes we have to use that there is no maximum for U. And that's the point. Assume for a moment that we have this strict inequality. This means that 1/2 x plus y satisfies the budget constraint corresponding to the price vector 1/2 P plus Q. But it cannot be optimal because there is no local maximum, as we reasoned yesterday in a similar situation. Okay? So this is impossible. And we have really almost finished now. The only thing that is left is to write 1, the number 1, in a clever way. Can you suggest a clever way of writing 1 in this context? I'll tell you one. This is equal to 1/2 Px plus Qy, because Px satisfies the budget constraint, X satisfies the budget constraint under P because it's optimal for P, then it is feasible, and cannot satisfy it strictly because U has no maximum. Okay? So this is equal to 1, and this is equal to 1. And this is the end of the proof, because this inequality is equivalent to the monotonicity condition. This is, so you multiply everything with 4, then you get P plus Q x plus y greater than or equal to twice Px plus Qy. Okay, and then you move things from this side to the other side. You get Px, because you have 2 here, minus 1 coming from the left-hand side. The same with Qi, and then subtracting you get Py plus Qx less than or equal to 0. And of course, this means that P minus Q x minus y is less than or equal to 0, which is the monotonicity condition. Do you agree? Is it okay, this proof? Any problem? No? So I think mathematically it's a very beautiful result because the statement is very clean. The proof is very simple, but not routine. Okay? But from an economic point of view, it's meaningless. Even though it was obtained by an economist, not by me. Okay, well, by me the refinement, but the basic idea by an economist. Why? Because assuming that a utility function is concave is economically meaningless. Okay, it simply means that the preferences are described by a convex total preorder. But the same preferences can be represented by another utility function, actually the composition of U with an arbitrary increasing function, strictly increasing function, for instance. And such a composition will not be concave anymore. It will be just quasi-concave. And then, so this assumption does not tell anything about your preferences. The fact that instead of quasi-concave you can write concave doesn't tell us anything. Exactly the same with convexity of indirect utility functions. Utility functions are always quasi-convex, always. But they are convex by accident. And also, of course, the indirect utility function depends on the direct utility representation. So for some use representing your preorder, V may be convex by accident, and for some others not. So it's equally meaningless from an economic point of view. But as we're going to see sometime later, in fact, this somehow is showing the difficulty of the issue, because somehow concavity of a utility function and convexity of the indirect utility function are opposite assumptions. In a sense, it's not exact what I'm going to say, but the more concave U is, it's more difficult to get V convex. Okay? So these conditions point into different directions. If you succeed to give me a concave utility representation of your preferences, it is unlikely that the indirect utility function is convex. So these assumptions are not totally contradictory, but let's say partially. The difficulty is to find, finding a concave utility representation is not difficult in most cases, because many quasi-concave utility functions can be concavified. This means you can find, not everyone, this means you can find a strictly increasing function such that after composing this function with your utility function, it becomes concave. This is very frequent. It was studied first by Yanai, then by Jean-Pierre Crouzet, of course. In his thesis, he gives a theorem which is a necessary and sufficient condition for concavifiability. Well, in his case was for convexifiability, because he was working with quasi-convex, but we change signs. and nothing happens, which I consider very important. And I asked him, but this is unpublished. And I asked him, why didn't you publish such an important result? He said, because the proof is 50 pages long. Such a non-trivial result. 50 pages long. It's hard to get a 50-page long proof published. Okay, so having a concave view is not hard. Very frequently, your utility function can be concavified. But then the trouble is that at the same time U is concave and its associated indirect utility function is convex. However, it happens sometimes. We have seen at least one example in which the utility function is concave and the indirect utility function is convex. What? Leontief, exactly. So with Leontief, the utility function is minimum over I of xi over I with ai positive. This is concave and linearly homogeneous, positively homogeneous of degree 1. And V of P is 1 over PA. And this is convex. Do you agree? How do you know that this is convex? Because this is H of PA with H of T equal 1 over T. T positive, because PA is positive. So this H is convex. And we are composing it with a linear function. Then it is convex. So that exceptional situation occurs sometimes, for instance, in the Leontief case. Is it easy to see directly that a Leontief demand is monotone? Well, we observed that for Leontief, when the price of good I increases, the demand of that good decreases, not only of that good, of every other good. But this is not enough for monotonicity. Monotonicity is more than this. It's a condition, it's that condition with the inner product, okay, which is stronger. Let's see if it is easy to see. We observe that the demand of corresponding to the price vector P is proportional to A. So A is the vector whose components tell you what you should buy of each component, of each ingredient, to produce 1 unit of food, of your food. Okay, so this is proportional. Simply, you buy the goods in proportion to the way they enter in your recipe, and then you normalize in such a way that you spend 1, which is your budget. So, suppose, well, now because it's a demand function rather than correspondence, instead of x belonging to f of p, I can simply write x of p. Okay? Thank you. So, what is x of p minus y of p times q, not p, times p minus q. This is 1 over pa a minus 1 over qa a times p minus q. Is it correct? And this is 1 over pa minus 1 over pqa product a p minus q. So in the end, what you get there is an error sign here. No. So in the end, what you get is minus PA minus QA to the square divided by PA times QA. You have a square in the numerator and two positive numbers in the denominator and a minus sign here. So this is less than or equal to 0. So as you see, it's very easy to check directly that a Leontief demand is monotone, as it should be because of this theorem. Well, so the story is, I found the paper, the unpublished paper by Millerand. I refined his statement and his proof. I was happy, but I said, can we go beyond? Look at this simple proof. Can you go beyond? There is an apparently easy way to go beyond, but it's only apparent, which is to say, look, here the concavity and convexity conditions, I am not using with arbitrary lambda between 0 and 1, but just with 1/2, both here and there. So instead of assuming concavity, I could assume what is called midpoint concavity, but this is not a real relaxation because U is defined everywhere, in particular on the positive orthant. Then it is continuous there. And for continuous functions, there is no difference between mid-concavity and concavity. Because every lambda, but it's an easy continuity argument. If the condition holds for lambda equal 1/2, it can be easily proved by induction that it also holds for every rational number quotient of two integers in which the denominator is a power of 2. And such rational numbers are dense in the reals. And then by continuity, you get that the result holds for every lambda, just assuming midpoint concavity. So this should not be a real relaxation. But can you refine that proof to make a substantial relaxation of the statement? Actually, you can do a lot more. And this is the advantage of simplifying proofs. It's just concentrating in the essence of the proof, leaving aside details. And then you, sometimes, not always, you can make some progress. Okay, if you look at the original proof by Miller-Legaz, it's impossible to go beyond. There are too many, not too many, but many unnecessary details. But now this is the essence of the proof. There is nothing superfluous in this short proof. Then, consider the following function. Of two variables, Px, prices, commodity bundles, U of x minus V of P. In fact, all that proof goes through if we simply assume that psi is quasi-concave. And we will then comment about the relations between these two assumptions. How would we write the proof under this assumption, the same proof? We would say, okay, instead of starting with 1/2 x plus y, I would start with the 1/2, the sum of px plus qy, and apply it to p. And because I am assuming quasi-concavity, yes, of psi, this is greater than or equal to the minimum of psi of px and psi of qy. And this is 0. Okay? Because ux is equal to Vp. We already use it here. And uy is equal to Vq, which we already used. And then, because this is u of, by definition of psi, 1/2 p plus q, 1/2 x plus y, minus v of 1/2 x plus y, we reach the conclusion that commodity bundles are here and prices are there. Now I think it's correct. Okay? I'm just using the definition of psi. And we are saying that this difference is non-negative. So we arrive at the same conclusion as here. U at the midpoint is greater than or equal to V at the mean point, and then we can end the proof in the same way as we did here. Okay, once we arrive to this point, we continue. So now, how weaker is the assumption that psi is quasi-concave in relation to the original assumptions that U is concave and V is convex. It's weaker, but not much weaker. You know why? There is a result by the Nobel laureate Gerard Debreu, which Jean-Pierre Crouzet improved, substantially improved, in a joint paper with Lindberg, a Swedish mathematician, long ago, in which the result is as follows. Suppose you have a function f of x1, xn, but be careful, now x1 is not a number, it's a vector, so all these are vectors. Xi belongs to R, let's say pi, are vectors of different sizes. And suppose the function is separable. So this is written, this can be written as a sum, this is the sum, and n is not the dimension of the space, so let's say m of functions of this each group of variables. Okay, you have a separate. You understand? So I have a function f of x, y, z. X, y, z are vectors, which can be written as f1 of x plus f2 of y plus f3 of z. So it's a separable, it's additively separable function. Then assume that the sum is quasi-convex. Well, we're dealing with quasi-concavity, but we just need to change signs. Suppose f is quasi-convex. You make this operation, and you happen to get a quasi-convex function. Then each term in this sum, except at most one, is convex. By the way, we never discussed about additivity in connection with quasi-convex. Convex functions are very nice. The sum of convex functions is convex. A sum of quasi-convex functions is only exceptionally quasi-convex. Normally, the sum of quasi-convex functions is whatever you want. Look, for instance, at the real line. What is the sum of quasi-convex functions? Quasi-convex functions are monotone. If you sum an increasing function with a decreasing function, that is to say, you are subtracting two non-decreasing functions, what can you get? Any function of so-called bounded variation. A very large class of functions. So, adding quasi-convex functions, you can add if you want, but you lose quasi-convexity. And the same with quasi-concavity, of course. In fact, Jean-Pierre Crouzet, who else is not, if not, proved a very nice, easy to prove result saying, suppose you have a quasi-convex function such that this can be done as an exercise. I think I could do the proof if you request it. You have a quasi-convex function, and whenever you add to it a linear function, you get a quasi-convex function. Then your original function is convex. I repeat, you have a quasi-convex function. And whenever you add to it a linear function, you get a quasi-convex function. Just linear you are adding, not an arbitrary quasi-convex, just linear. Then your function was convex. And of course, then convex plus linear is convex. But that's the only way. Said in other words, if you have a quasi-convex function which is not convex, you can always find a linear function such that adding the two functions, you don't get a quasi-convex function. So this means that additivity and quasi-convexity do not behave well with each other. Okay, but here, so you are having a sum of separable functions. This is a very particular case. I mean, a separable function, so it's a sum of functions, each one of its own variable. And the sum happens to be quasi-convex. Then, well, since we have just seen the limitations of addition in connection with quasi-convexity, we are not so surprised to see that this can only happen somehow exceptionally. And the exception is all the terms in the sum, except at most one, must be convex. And the one who may fail to be convex has a degree, has a bounded degree of non-convexity. There is a way which he did to introduce a notion of degree of non-convexity for a quasi-convex function. Okay, and he said, okay, the one which is not convex cannot be too far from being convex. Okay? Its degree of non-convexity is bounded by some specific bound that he obtained. Okay? Is everything clear? Then now compare. What we are adding here is of course, the same can be said with concave. So this psi is y plus minus v. This is a separable function because u depends only on x and minus v depends only on p. Then, if this is convex or concave now, quasi-concave, if this is quasi-concave, at least one of the two must be concave. So, either u is concave or minus v is concave, which means v is convex or both. Okay, and the degree of non-convexity of the one or non-concavity of the one that fails to be concave is bounded by a precise bound. Okay, so this is a relaxation, but not very spectacular, because still, in a hidden way, you are using the unpleasant assumption that the utility function is concave or the indirect utility function is convex, although you don't state it like this. So, okay, we made some improvement, but we didn't go very far. Now the question. So, this is the second refinement of Milleron's proof. My first refinement and refinement of my refinement. Now it's your turn to refine this second refinement. What do you see? Are we really using quasi-concavity of psi? We are using it, but could we use less? What is quasi-concavity? Is convexity of the upper level sets. And here we have used only convexity of the zero upper level sets. Okay, so we have taken 2 points, Px and Qy in the upper level set of psi level 0 because they satisfy psi of Px and Q of and psi of Qy equals 0, and then we have used that the midpoint is also in that level set. This means that psi is greater than or equal to 0, so we have not used the full power of quasi-convexity, which is convexity of infinitely many level sets. We need only convexity of one upper level set. And this is really a very substantial improvement. So look how far can we go with simple arguments from a proof that you have not seen in the original paper of Leontief after clarifying its real meaning, its real essence. So, you will not find any of this in any publication except without proofs in a chapter I wrote in the Handbook of Generalized Convexity and Generalized Monotonicity. But except for that, all these results I'm telling you are unpublished. So there is maybe room for improvement. So, okay, well, I erased the definition of psi. Our last conclusion is that the upper level set of psi corresponding to level 0 is convex, implies that the demand is monotone. So here the limitations that a sum of quasi-convex functions of different variables is only exceptional quasi-convex, all the terms except at most one must be convex, etc., does not appear. Okay. But what is this set? Let us look at this set. This set is the set, of course, the set of pairs Px such that u of x is greater than or equal to v of p. Okay? Psi greater than or equal to 0, which is the condition of belonging to this level set, means simply that u is greater than or equal to v. U of x greater than or equal to v of p. No. No. I have defined psi for arbitrary p and arbitrary x. Okay? And now I am looking at the upper level set of this function. Forget the demand. We don't need to look at the demand when we are examining psi. You have a function, you have its upper level set, apply the definition of upper level set, and you get this. The demand plays no role here. Okay? So I'm talking about the assumption, not about the result, which implies monotonicity of demand. Do you agree? And does this condition say anything to you? u of x greater than or equal to v of p? Any economic interpretation? Or look at the definition of v of p. V of p is the supremum of u of x subject to px less than or equal to 1. So, if you replace v of p with this definition here, of course, u of x being greater than or equal to the supremum means u of x is greater than all these numbers. It's better to change the notation here because x is already used. So let's write whatever you want, y instead of x. Okay. Pay attention. Y satisfies the budget constraint. X does not need to satisfy it. Okay? Do you think something very interesting in this expression? I'll tell you what. That it, do you see anything? That it is independent of the utility representation. It depends on preferences only. So u of x greater than or equal to u of y simply means that x is preferred to y. And this happens, the inequality happens for every u. So this is a condition just for preferences. So we are now about to obtain the only result I am aware of stating monotonicity of the men without utility representations. It's not a very powerful result because the assumption is very strong, but it's something in the line I was looking for. I said the conclusion that the demand is monotone is an algebraic conclusion. Then differentiability, etc., these are tools to prove monotonicity, but it's not in the essence of the problem. I still want to obtain, but I will never succeed, an algebraic necessary and sufficient condition for monotonicity of demand. Well, here we have such a condition that we already refined, but still with utilities. But now we can move to a more general context, the context of non-necessarily representable preferences. In that context, we can introduce demand correspondences and prove monotonicity of demand. Of course, when I was relaxing the assumption that U is concave and V is convex, then I did it. But the standing extra assumption was that U has no maximum. Okay, so the results would be if U has no maximum and this is quasi-concave, then the demand is monotone. Or if U has no maximum and this upper level set is convex, then the demand is monotone. But I cannot get rid, and I don't need to get rid of the assumption that U has no maximum. But now let us forget for some time about utility representations. Our preferences are as consumers are given by a total pre-order, not necessarily representable. It could be the lexicographical order, for instance, which is not representable. Then, given a price vector, we can define the demand correspondence. Okay? X of P is the set of X in R plus C, R plus N, that satisfy the budget constraint under P, and R preferred to any other commodity bundle that satisfies that budget constraint too. Do you agree with this definition? Of course, if your pre-order is representable by a utility function, that's the same, because this means U of X greater than or equal to U of Y. So U of X is the largest value, X is feasible, and U of X is the largest value in comparison with all the other values at feasible points. Okay? So we have a natural notion of demand correspondence, so we can talk about the monotonicity of such a correspondence. And then let us consider this set, which depends on the preferences. I'm going to call it C, subindex the preference because it depends on it, is the set of Px in R plus N cross R plus N such that U of X is greater than, sorry, there is no U, such that X is preferred to Y for every Y such that Py less than or equal to 1. These two definitions are together and look very similar, but they are quite different. First of all, here we have elements in R plus N, just commodity bundles. In the second set, we have pairs, prices, commodity bundles. Moreover, another important fact is that here X satisfies the budget constraint and here not necessarily. Okay? Set of pairs, prices, commodity bundles. Does it have any economic interpretation? Yes, and very clear, in a sense. It's the set of pairs, price commodity or price bundle, such that you prefer that bundle to that price. How can you compare commodity bundles with price vectors? You do. So suppose one day you are at home and a salesman knocks your door and says, "Good morning. I have this commodity bundle here and I offer it to you for 1 rupee. Would you accept his offer or not?" If you are a rational consumer, you'd reply, "Please sit here, wait for a moment." Then you will go to your room, open your laptop, and check the prices in your neighboring supermarket. And you will see what you can do with the 1 rupee he is asking you in that supermarket. If it happens that X, which is what he is offering, is better for you than anything you can buy in the supermarket where the prices are P, then you go back to meet him and say, "Thank you, I buy it." Okay? So this means you prefer his offer, X, than going to the supermarket P. No. X does not satisfy. Well, X satisfies because he came and told you, "I offer this to you for 1 rupee.
But here there is no condition on X.
Here there is no condition, but P is given.
But that can exceed the rupee 1.
In which way? With the salesman?
With the salesman.
No, because he is offering you it for 1. You will not bargain with him saying, "I offer you more than 1 rupee. He is offering this to you for 1 rupee. Okay? Because, excuse me, because you are in the end you are comparing this with what you can buy in your supermarket with 1 rupee. This comparison makes only sense if what he is offering you, he demands you to pay 1 rupee. What were you about to ask? I interrupted you.
So in the C set that we have defined, though we are comparing X with the Y, and Y is corresponding so that the price will be 1, but there is no condition on X. So,
Exactly, there is no condition.
so does that comparison with the preference with Y giving us some condition on X with respect to the price? Because the example that you have considered, like that is corresponding, the price is the X is offered some quantities with respect to the price that is corresponding to rupees like cost 1. But in this set C there is no condition. So
Okay, let me express it in a different way. So there is no salesman. Okay? Then you consider some commodity bundle in your mind that you may like to buy, but you don't care about its cost in the supermarket. You don't care if it costs 1 rupee less or more. Okay? But then you compare it with everything that you can afford in your local supermarket. If it happens that it is better than anything you can get in your local supermarket with 1 rupee, you would be ready to pay 1 rupee for it. So now I am the salesman, I knock your door, and now it's now when I offer you this, your dream commodity bundle for 1 rupee. Okay? So, I mean, this set has some economic meaning. And we are going to assume its convexity. Okay, it's going to be an assumption. So I need to give another definition, because I insisted that in all these relaxations of the original result, we always had to add the assumption that U has no local maximum. But now we have no U. I cannot talk of local maximum. So what is the assumption of no local maximum in the case of preferences? This is what economists call the local non-satiation property. Roughly speaking, it means that for every commodity bundle in the neighborhood, no matter how small the neighborhood is, you can find something which you strictly prefer to that. So you are never satiated locally. The formal definition is this is locally non-satiated means for every x and for every positive epsilon, there exists x sub epsilon in R plus n intersection the ball with center x and radius epsilon, open ball, or closed ball, doesn't matter, such that x prime and x epsilon is strictly preferred to x. If your preferences are represented by a utility function, this means that your utility function has no local maximum. Any utility representation. So if it holds for one, it holds for any. Because it's a property not of that particular representation, but a property of your preferences, okay? Because in case of a utility representation, this means U of x epsilon greater than of U of x. And this is the meaning of non-being a local maximum. Okay, so what we will, in fact, we had already proved it, but since we have made a long way from the initial assumptions to here, it's good to check if we didn't miss something on the way. So after the break, we will check that and this is a very realistic assumption, because normally if I offer you a little bit more of every component in the bundle, then you would be better off, strictly better off. You'd prefer it. Okay, so this is not something very tricky. So suppose that your preferences are locally non-satiated. And this set is convex, then the demand is monotone. We have seen that, but we will make a direct proof just to check that we are not missing any detail. Okay? Is clear? Should we stop now?